So in a previous lecture, we have discussed different high pressure gauges like burden pressure gauge, diaphragm pressure gauge, bellow pressure gauge, then simple mechanical ring gauge. Then we have also discussed about deadweight tester, because that you have already used in your laboratory session. So you are familiar with the entire setup. Now in today's session, we'll be discussing low pressure gauges which are used for vacuum pressure measurement. So pressure below 1 mm of Hg, that is termed as a vacuum pressure. So general unit for vacuum pressure measurement is torr. So 1 torr is equals to 1 mm of Hg, and that's why 1 micron of Hg, that is termed as a 10 is to minus 3 torr. So this is just a basic unit conversion, and these are the different ranges of vacuum which are listed here. Then the classification of vacuum pressure measurement instruments, then direct measuring instruments like manometers, bellow, burden and diaphragm gauges. So this we have already discussed in our previous lecture. So today we'll be discussing some indirect instrument for vacuum pressure measurement. In that we have McLeod gauge and thermal conductivity gauge. So these two we'll cover today. So first of all, McLeod gauge. So let us try to understand basic construction of McLeod gauge. Here we have a mercury reservoir and piston arrangement. Then we have a capillary line here. So this end, from where we are getting two branches of capillary tube, that is called as a cutoff point. And this column, this is called as a reference capillary. And this open end, that is actually connected with the source, which pressure you want to measure. The vacuum pressure which you want to measure, that is connected at this open end, right? Similarly, the second branch that is having very large volume, which is called as a bulb, right? So then bulb, and then this again one capillary, which is called as a measuring capillary, where we have graduations. So on both the capillaries, this is called as a reference capillary and this is called as a measuring capillary. On both we are having graduations, right? So top portion or the topmost graduation, that is called as a zeroth graduation in both the capillaries, right? So I think basic construction is clear. Now what we need to do is when we keep this piston at the bottommost position, then at that time this mercury should reach up to 0 0 at this position. It should reach up to 0 0 in both reference capillary and measuring capillary, right? Now what we'll do, we'll pull this piston up. So so the mercury which is at 0 level, that will come down, and this we need to do until we get mercury up to the cutoff point, right? So what happen is, this both reference capillary and measuring capillary both are empty now. Now just connect your vacuum source here. So because of vacuum, now this entire capillary portion, that will be filled. So this reference capillary as well as this bulb and measuring capillary, this entire portion which is above cutoff point, that will be filled by vacuum, right? Now what we'll do, now we'll just close this end, we'll remove that source and we'll close this end, and again we'll push this piston down. So as we push this piston down, then mercury will again go above this cutoff point, and we need to push it down until we get mercury up to the 0 reference in the reference capillary, right? So what happened due to this, the vacuum which is filled within the capillary, that will compress this measuring capillary. So here you can see this blank portion. So that blank portion is the vacuum after compression, right? And this H is the pressure of vacuum after compression in terms of mm of Hg. right? So I hope working of this McLeod gauge is clear. Is there any query in working of McLeod gauge? Okay, so now according to this, if you look initially when Hg is at cutoff point, vacuum at pressure P0 fills the total volume V0. Means when this mercury is at cutoff point, then this entire system that is filled with the vacuum and whose pressure is P0. Now we want to find out how much the value of this P0, because P0 is the vacuum pressure, right? So P0 V0 is equals to constant. Okay, and this V0 is the total volume, volume of bulb and volume of this measuring capillary, right? Now in the second half, what we'll do, we compress this mercury and we'll lift this mercury level up to the zero graduation in the reference capillary, right? So because of that, what happened, the vacuum which is filled in bulb and measuring capillary, that will compress, right? So that is what discussed here. Now when mercury reached to zero in reference capillary, vacuum compressed to pressure PC, this is the compression pressure, and within volume VC in the measuring capillary. So this H into area of measuring capillary, that is the volume VC, right? So PC VC is equals to constant. So here this PC stands for vacuum pressure after compression and VC stands for this height into area of measuring capillary, right? Now this compression is isothermal compression as per Charles law, right? So that's why we can equate this two, because there is no change in temperature, right? So P0 V0 is equals to PC VC, right? So now after compression, pressure indicated by measuring capillary is a differential pressure. If you look here, this H is the mm of Hg. So that indicates what? That indicates difference between vacuum pressure after compression and initial vacuum pressure. So Pc minus P0 is equals to actually this H, which is indicated in the measuring capillary. So from this we get Pc is equals to P0H, right? Compression pressure is equals to vacuum pressure, initial vacuum pressure, plus this height in the measuring capillary, right? Now what we'll do, we'll put this Pc in this equation and we'll try to form equation of P0. So we are getting this equation, P0 is equals to AH square. So this AH square is nothing but this here if you simplify this P0 equation, then you will get this equation AH square divided by V0 minus AH, where V0 stands for total volume of bulb and measuring capillary, A stands for area of measuring capillary, and H stands for this height of compressed vacuum, right? So now as you look, this A by H, A into H, volume of measuring capillary is very less compared to the volume of bulb, right? So we can say V0 minus AH is equals to V0 approximately, right? So this P0 is equals to AH square by V0. So this is our final equation after this assumption, because volume of measuring capillary is very less compared to the volume of bulb, right? So this is the final equation which can give you vacuum pressure from the bulb, from the McLeod gauge, right? So now pressure is calculated from physical dimension of gauge. There is therefore there is no issue of ambient effect, surrounding effect, because pressure is not measured with reference to some atmospheric pressure or any other quantity. It is merely based on the dimension of gauge, right? Hence can be used as a calibrating instrument. This can be used as a calibrating instrument, because here you not required any correction of ambient effect. right? Continuous monitoring is not possible, means if you want to install this McLeod gauge to see the fluctuation in the vacuum pressure, then that is not possible because it is indirect approach based on the measurement of H and the dimension of other in the dimension of this McLeod gauge we are getting this pressure. So continuous monitoring is not possible. Remote reading is also not possible, means you have your application somewhere else and you want to do measurement at some other location, then that is not possible. Gas should obey Boyle's law because that is the main assumption here behind this derivation. And V0 by AH should be large enough, but tube diameter should not less than 1 mm just to avoid that capillary effect, right? So these are some important points or limitation we can say of this McLeod gauge. Advantages: independent of gas, it should not contain only vapor portion in it, so that compression is possible. Otherwise, if vapor comes, then compression would be difficult. So that's why we get some error. Measuring range, that is 1 torr to 10 raised to minus 2 micron of Hg. So some simple example based on the equation which we have derived for McLeod gauge. So McLeod gauge is available which has bulb and capillary volume up to 0 level 200 centimeter cube. Capillary area is 0.1 centimeter square. Calculate the gauge reading in micron for pressure of 1 centimeter in capillary. So if you try to understand what this data, then this 200 centimeter cube is V0. Small a, capillary area, means small a is 0.1, and H, value of H in measuring capillary, that is 1 centimeter. So these three details are given. So now you can use this equation because A is given, H is given, and V0 is given. So you can find out this P0, which is vacuum pressure. So if you solve, you will get 5 micron after solving this. Okay, so you can try, you can note these values and use that equation. So you'll get 5 micron value. In line with same, we have another problem. McLeod gauge has a volume of bulb and measuring capillary is equals to 110 10 to the power minus 6 meter cube. So this is again V0 given. Measuring capillary diameter is 1.1 mm. So based on diameter, we can calculate area, right? So you can get small a from this 1.1 diameter, right? Now calculate the pressure indicated when the reading of measuring capillary is 28 mm in case approximate formula is used, right? So H is 28 mm. Second case, what is the error if the exact formula is used for pressure measurement? So if you look, we have used, so here we have two formula. This is approximated formula based on this assumption, right? And this is the actual formula. So as per the case A, we need to just find out P0 using this approximate formula. And in case B, we need to find out error, means use this equation and find out P0, just get difference between these two, that will give you error, right? So again, a problem is simple, based on equations you can solve because other details are given. So answer of question A, you get 6.773 micron, and after solving B, if means after the answer of B, that is 0.002 micron. This is the error based on the assumption which we have taken, right? So this is all about McLeod gauge. Next is thermal conductivity gauge. So at low pressure, at vacuum pressure, heat conductivity directly proportional to pressure. Means higher the pressure, higher the conductivity, right, of the element. So same principle we are using in thermal conductivity gauge. Filament is heated with constant electric supply. So we are continuously heating filament with constant electric supply. Now temperature of filament is function of two quantities. One is heat supply and second is heat dissipation from the filament, right? But if constant current supply, then temperature is only function of heat dissipation, right? It is only the function of conductivity, thermal conductivity. Okay, so based on this principle, this instrument work. So lower the pressure, lower the surrounding pressure to the heated filament, then lower the thermal conductivity, and higher would be the temperature, because heat dissipation from the filament will be less because of the lower pressure. So based on this hypothesis, this instrument work, right? So here we are measuring pressure in terms of temperature of filament. So pressure can be estimated by temperature, measuring the temperature or resistance. So this is the arrangement. So we have a vacuum chamber in which we fill our source vacuum whose pressure we want to measure, right? Here we have the filament, and this filament is continuously heated by constant current source, right? Now to measure temperature of this heated filament, we are using thermocouple, right? So this thermocouple, as you already know the principle of thermocouple, based on the EMF we can measure temperature. So we have here one voltmeter to measure the voltage, right? So what we do is, if the vacuum is having less pressure, then there will be less heat transmission or less heat dissipation from this heated filament to the vacuum, and that's why temperature of this filament will be more, and this temperature will be measured in terms of EMF using this thermocouple, right? So this is the setup. Now suppose if you want to measure resistance, then you can use Wheatstone bridge circuit, because as you know temperature will change resistance of metal, right? So that's why we can use Wheatstone bridge circuit, and we can measure resistance also, right? Now if you see the measuring range, then it is from 10 is to minus 5 tar to 1 tar, right? It cannot use beyond 1 tar because of the saturation. So here you can see, if you go beyond 1 tar pressure, then there is no change in the Wheatstone bridge current or resistance. So that's why their use is limited up to 1 tar. Now let us see one video demonstration on Pirani gauge. So is this video VLC player is visible?
Yes, sir.
Yeah, and please also tell me about audio. Audio is available?
Guys, welcome back to Pulse Check.
Okay.
Got a new video here. I'm going to be talking about the Pirani vacuum gauge that I've made here. This is a brand new piece, and it's really exciting what we can do with it, because it allows us to precisely measure vacuum level in the chamber in real time. So let me just go over a little bit about how this works. Basically, we've got a light bulb filament inside here, which is attached through terminals that are sealed, and when you supply power to it, voltmeter is set up in series with the filament, so it's reading the current draw on the filament. And what that means is that basically this is an indirect measure of the temperature of the filament, and because it's being heated by the very small electrical current that we're supplying, the temperature will depend on the pressure of the gas surrounding it, because obviously the gas is going to be absorbing heat from it. Now we can demonstrate that by simply blowing air across the filament and observe the change in the reading. So you can see a huge spike in the reading there, a huge increase in the current draw, because as I blow air across the filament, that's cooling it slightly, which is decreasing the electrical resistance, therefore increasing the amount of current that it's drawing at that point in time. Now the way this works is that normally this piece is fitted inside this connection, which is very well sealed and integrated into the vacuum chamber itself. So that now we can use this gauge to determine what pressures we're looking at inside the chamber. So I could just demonstrate that by flicking on the pump, make sure that the valve is closed here. Now you're going to see the reading spike at first, and that's totally normal. That's not because of a change in pressure per se. That's because simply pulling air out the bottom, you're getting a small flow across the filament, which cools it. After that spike, it will steadily drop as a result of the pressure dropping. So let's see what happens. Okay, now the pressure is steadily dropping, and we can see that very easily in the readout. This should drop down well below 34 milliamp level, and the bottom, the minimum reading will vary based on ambient temperature and a couple of other factors, but basically this is for something that's completely homebrew. It's actually a really nice tool for us. So I'll let this reading just kind of stabilize, reach its minimum. Okay, that looks good enough. Okay, now going to crack the air inlet slightly and observe the reading. Now you can hear the pump sucking air a little bit. See that reading start to rise as the pressure rises. And that's only a very small change in pressure, because this gauge is extremely accurate, extremely fine resolution, low pressure environments. Now I close it back down. Now we can watch the pressure steadily return to the minimum that it was at before. So that's basically how the thing works. Nothing more than a light bulb filament, some PVC pipe, plastic jar got from the store, and yeah, this will be really useful in a lot of the testing that we'll be doing. So that's basically it for this setup. Thanks guys for watching. Hey guys, so I just wanted to talk for a second about how the kind of stabilize, reach its minimum. Okay, that looks good enough. Okay, now going to crack the air inlet slightly